Hello, welcome back to another class of Transformer Encoder, Part 3. Part 1, we talked about Transformer in general, which has two parts, encoder as a reader and decoder as a writing output. And then Part 2, we talked about um, the input. We talked about the embedding input and positional embedding. So we mainly talked about this part, and we explained this part with the example that we have. And part one of previous class, we talked about encoder, this one, and decoder in brief. Now we're going to talk about, in this class, we're going to talk about this part. Let me highlight in black. So we're talking about this part, multi-head attention. So we're talking about this part, multi-head attention, in this class. Now, recap from the part two that we found the uh, input. We found this part. Okay, this part was Z, uh, which was embedding plus positional embedding input plus positional embedding. So we found this one, which was 3 by 4. Three tokens we have, 4 dimensions or 4 features. And the sentence was, I like Rojava. Now the self-attention, which is we're going to work with multi-head. Um, we were talking about, we're working with multi-head attention. So here we talk about the self-attention, which has three. We need to create a query, key, and value for each token. So each token must have these 3 elements. So attention is computed as softmax, the function uh, qk uh, uh, k transfer over square root of dk multiplied by the v. So that's we need to find the word and the relationship of the word with other words, which are very, very important. Now, so here we will create a weight matrix for Q, for K, and V. And we have uh, dimensional model is 4, and dk, which would be reduced from d model would be reduced to dk by 2 dimensions. So we will have weight matrix 4 by 2. It means we have 4 rows and 2 columns. That's what we are going to do. So we create WV, WK, WQ. Each one of them is 4 by 2. So this is 4 rows by 2 columns, 4 rows by 2 columns, 4 rows by 2 columns, and this is randomly is assumed. Each one of them is assumed randomly. Now let's do the compute Z, the the input that we have it, multiply by weight matrix Q, because the Q was 3 by 4 and WQ is 4 by 2, so the inner will be uh, will be removed, and we should have the product of 3 by 2 matrix. So let's do it for token 1I, which is the first row input multiplied by Q. So 0.2 multiplied by 1, that's 1. And then 1.1 multiplied by 0, and so on and so forth. So that's for the first row, the Q was found 0.9, 2.4. Now we do it for the like. Again, like has, that is the this one, this row. We'll do it again for multiplied by the first column and the second column, and we will get two values again. So done, two values was found for like, and we will do for Rojava again. Rojava, the row number three, this row multiplied by the first column and multiplied by the second column, you'll have two values. Now, that's what we said. So if we have, that's the Q, and Q is now 3 by 2, as we mentioned, because it was 4, I think 3 by 4 and 4 by 2. It was 3 by 4 and 4 by 2. So 4 will fall. The inner dimension will go, only the outer dimension will be considered. So that's for Q. Similarly, we do it for Z multiplied by WK for the K. Likewise, the Z, the first column multiplied by the first row multiplied by the first column of the W, and multiplied by the second column of W, and we find K for the first and second token and third token. So likewise, we do it for WV. We will have, that's WV. If we go back, we'll do it for this one. The first row of the input multiplied by this, and the first row of input multiplied by this, the second row of input multiplied by this, and the second row of multiplied by this. So likewise, we will get the V as well. So that's V found, Q found, and K found. Now, here is the results that we have for each token. We have query, K, and value. Now, we need to compute this formula, softmax, Q, KT over square root of dk multiplied by V. So we have Q, we have K, we have V, and we will have dk. We have d model 4, and dk is 2. Square root of 2 will give us 1.44. That is the results that we have. Now, here we have to QK. So we have K, and the transfer of K, that's K. The transfer of K, it will be 2.4, 2.389, and 1.37, and 0.9, 1.55, and 2.3. So that's KT, transfer of K. That's what we got it, this one. And then we multiplied by Q. And Q was 3 by 2. So 3 by 2 multiplied by 2, 2 rows. This is 2 by 3, 2 rows and 3 columns. So 2 with 2 would go. We should have a matrix 3 by 3. Now we find we have 0.92. We multiplied by this one and this one. So 0.9 multiplied by 2.4, and 2.4 multiplied by 0.9. That's how we got for the same column, 0.9 multiplied by 0.9 multiplied by 2.83 plus 2.4 multiplied by 1.55. That is 0.9 multiplied by 2.3 and 2.4 multiplied by 1.4. And then the last column, again, 0.9, this 0.9 multiplied by this, and 2.4 multiplied by this. So that's how we got it. So we got this results. Now, we will do it for row 2 as well, same thing. And we will do it for row 3 as well, same thing. Now we should have this for, that's for row 2. Now we should have row 3, same thing, and row 2 for the and column tree, and we will have row attention scores all together Q multiplied by T. That's the results that we have. That is the results that we have. So simple as that. Q is this one multiplied by this part and multiplied by this part and multiplied by this part. And then later on again, the second row of Q multiplied by this part, by this part, by this part. So that's how it worked. That's the second row of the Q. Uh, we did it. And then and for row 3, that's the second row Q3 multiplied by the KT. Now, this is what we found. Next, we need to get dk square root, which is 1.414. That's what we got. And then um, divide um, divide each column 4 point divide each cell by 1.414. So that's what we did, and here is the result. That's the scaling result. That's the scaling result. So following this equation, where is the equation? I should tell you. So where is the equation? I have this equation somewhere. Okay, that's what we did. That was what we did, following that one. Now, next we need to multiply it by V. Next we need to get the softmax for this part, and then after softmax we get the V. So just show you how to do it. Here we found the V, we found the dk, and then the QKT, that's the result. And now the scaling. So this has to be softmaxed right now. Each cell has to be subject to a function of softmax. Now, that's the softmax, the e to the power xi over sigma of exj. So here, e to the power this one, which is this, and e to the power this one, which is this, and e to the power this one. So sum of them, we sum them all, and then each cell divided by the sum. So for example, here 21.2 over the sum, 200.5, and then 84.6 over the sum, which is 200.5, and 105.7 again divided by 211.5. So that's the results that we get of the softmax. Now that's the results for the softmax for the first row. Likewise, we have to do for the second row. Again, this e exponential of this one, exponential of this one, exponential of this one, sum of them, and each one of them divided by the sum of the exponentials. So that is for the second part we did, second row, and likewise we have to do it for the third row. So that is the A matrix we found. That is the A matrix. Now, one note should be considered here. As you can see, the first row, 0.1 plus 0.4 plus 0.5, you should get 1. Likewise, 0.086 plus 0.51 plus 0.401, you should get 1. And likewise, 0.18 plus 0.685 plus 0.133, you should get 1. So some of them should give you 1. Now, here we can see that that I attends to Rojava by 50%. So we say that this is I, and this is like the second row, and this is Rojava. This is very important note. So I attends by 50% to the Rojava, 50% to the Rojava, I, the token I. And another thing here to be mentioned, that like like attend to itself by 0.51. So like attends to itself by 0.5. So like attends mostly to itself, which is the second row, which is like attend mostly to itself, which is the second row, second column. So this one we're talking about second row, second column, while the I here, first row, attends mostly to Rojava by zero point 0.5. And lastly, like here, the Rojava attends strongly to like. So this row, which is representing Rojava, attends to the second column of the row of the third row, which is 0.85. So what does it mean? Rojava attends to like mostly. So I hope it was clear, this one. This is what we talk about contextual representation. So the first row is I, which attends mostly to uh, by by zero point 0.5 to Rojava. Okay. And uh, in the second row, we can see a second row related to like. Okay. So like attends to itself by 0.5. And here, the highest is here 0.685 in this row. Means what? Means Rojava attends to like the second word. So Rojava attends to like. Okay. Rojava attends strongly to like. So that was uh, the the result of the representation of attention. Now we need to do A multiplied by V. We have A, we multiply by A. This one routinely can be done. So 0.10 multiplied by that one, zero point 0.4 multiplied by, and 0.3 multiplied by that one. So here, if we have, that is the uh, A, that is the A, we multiplied by I mean, zero point 0.1, zero point 0.4, zero point 0.5. So we multiplied by the V. And this is V, presents V. This is V. This is V. This is A, third column, cell. This is A, second column, first row. This is A, first row, first column, cell one. Likewise, we have to do it for the second column, and then the results will be that one. That's the final attention that we have. And we said it that I attends 50% to Rojava, like attends mostly to itself, because it was 0.51, and 0.6 something was Rojava attends strongly to like. So that is all about this. And what we understand from here is that um, we will use the same sentence. For example, I like Rojava, and the same encoder matrix 3 by 4. Now, why we use multi-head? That's the question. So this question is important. Why we use multi-head? Well, single attention learns one relation type. So when you have different heads, for example, head number one understands syntactic relation. Head number two understands the semantic relationship, and head number three and can understand other latent relationship. Why? Because you have different weight matrices. And now we mathematically concatenate head one and head two, and we multiply it by weight matrix output. For example, um, that's what we talked about it, how the two came. DK comes from D model. D model is 4, and we make it 2 heads, for example. Now, head 1 already done. That's the head 1, and we multiplied by Q. So previously we done. Now, if we want to create head 2, in order to create head 2, again, we have to design or initialize weight matrices. And that's what I put 2 here, means head 2, weight matrix for head 2. So for WQ2, WK2, and WV2. Now, again, similar things. We did Q1 multiplied by WQ1. Now we need to do for head 2, the Q2 equals Z multiplied by Q2, cube 2. So for the second head. Now, Z is not change, or the input that we got it from embedding plus positional embedding. That's the result. We multiply it by just um, new weight matrices for the three elements that we have, Q, K, and value. So for the first token, that's the result. That's Q2. And for the second row, we did it, assuming that we learned it from first time how we did it. So, and that's Q2. Now the Q2 was found. Likewise, we do it for K2 and V2, and we do the attention softmax as we did earlier. Similar to that, we get the scalar and we get the scalar and we get the softmax and multiply by V2. So that's head 2. Head 2 is found, which is 3 by 2, and we have head 1. Now we need to concatenate them. So that's head 1 that we found it, and that's head 2 that we found it. So we just concatenate them. We cannot average them because if you average them, we lose some information. We need different information. We have head 1 represents semantic, head 2 might represent syntactic, head 3 might represent other aspects of the grammar or semantic meaning. And we multiply finally by initialization weight matrix, which is 4 by 4, and we have 3 by 4, the head, concatenated head, multiplied by 4 by 4, which is W O, and this is the multi-head. So 3, we said that inner matrices will go, this one will go, so you should have 3 by 4 matrix. So at the end, WO multiplied by the Z, this one, which is the head that we have, we should get this result. So that's the final multi-head attention output, and this will be used for the next step or process. So just recall, each head created its own attention space. So each head has its own attention space because it has different weight matrices. Each head captured different token relationship. So for the first one, as we have 4 people, they're looking at the same sentence. So if I look at one sentence, I look at it from my perspective about that sentence. I might look at it from grammar point of view. So another person might, let's say I'm head 1. I'm looking at that sentence from grammar point of view. Mm, Another head, another head can look at it, another person can look at it from a semantic point of view. And the more heads you have, the more attention space that you create for the token. Now, each head captured different token relationships, and because of the different of weight matrices, so each token represents different attention. And then we concatenate learned relationship. Final linear layer mixes them, which allows parallel semantic extraction and richer contextual representation. And we have multiple relational spaces. We don't have one space. So we will have multiple relationships which are learned simultaneously at the same time, and we have richer contextual representation. Each token is represented from multiple perspectives and multiple relational spaces we would have because different heads specialize in different types of linguistic and semantic relationship. So this is all about today's class, about multi-head. What we did so far, I take you back. So what we did so far, we done with this one in the earlier part 2. We done with this one. now. So next we go to add a norm in the next class. So I hope it was useful and understandable and clear. So if you have any problems, please visit my website, and there are more information about this uh, topic. Thank you very much. Stay tuned for the next time. Thank you.